Vamos. A ver, un segundito. ¿Eh? No. Okay. One second. Okay, we can start. Hola. Buenas tardes a todos. Bueno, podemos continuar con las charlas que siguen. Presentamos en este momento a María Khodak, que bueno, va a estar continuando. Muchas gracias. La recibimos con un aplauso, por favor.
Hi, everyone. Thank you for coming in the rain to my talk. So today we'll be talking about data poisoning visualization using networks. I'm currently interested in the intersection of network science and cybersecurity, which is what we will look at today. My goal with this project was to figure out how we could visualize the data poisoning vulnerability in action if we visualize the graphical data that can be formulated from training data used to train LLMs. So machine learning models have become increasingly integral to many applications, including software applications, so they face increased risks from adversarial attacks as a result. What if we could represent that training data in a graph, and what if we could compare its data representation? Today, we will go further into that concept of data representation and provenance and how attacks can modify or poison data within networks. So, as a quick intro, here is who I am and a broad representation of my research interests. So I'm a security researcher and PhD student at Dartmouth College. A few of my research interests include binary analysis, specifically exploring graph theory, and machine learning and supply chain security. So, as a primer, what is data poisoning? Data poisoning is a very well-known machine learning vulnerability. As defined by OWASP, data poisoning is an attack that occurs when an attacker manipulates training data to cause the machine learning model to behave in some undesirable way. Typically, it occurs in three methods. So you have addition, modification, or deletion of data. Interestingly, addition can also often mean the injection of data, but injection attacks, as we know, do not always mean adding data. So moving on from data poisoning, we should first seek to understand how machine learning works. So how does it work? In this year, most of us know how machine learning works at a simple level. Machine learning is a method of teaching computers to effectively pattern match and make predictions from data without being explicitly programmed to do so, well, for each specific task. So algorithms learn from examples in the form of training data and to identify patterns, and once trained, models can make predictions off of new and unseen data. In this generalized example, there are three main types. So there's supervised learning with labeled examples, unsupervised, which would indicate the model would be finding some kind of hidden pattern, and reinforcement learning, which is learning through trial and error. And these applications often power systems like recommendation systems, image recognition, and language translation. So how does data poisoning fit into all of this? Here, I changed the diagram a little bit to accommodate data poisoning, and the model reflects poisoned data. Poisoned data goes into training data via an attack vector, and the machine learning model, or the algorithm rather, processes this data, and then the training model is compromised. And what this all leads to is biased output from the model, and ultimately the model doesn't fit the intended context of its stated purpose. So moving forward, I want to discuss a very famous and well-known example of data poisoning that violated this intended context of the model. How many of you know who this is? Anyone? This is Tay, a Microsoft chatbot that was released on Twitter in 2016. Tay was designed to pick up our language and syntax via interactions with real people on Twitter. Long story short, within a few hours of launching, it started repeating vulgar and hateful language. The important thing to note here is that the intention of the chatbot was to be fun, conversational, like a conversational agent, essentially. But after training on bad data, it became adversarial, tweeting hateful language, which was the opposite of its original intent. As malicious language was injected into the model, this is an example of a large-scale data poisoning vulnerability. An even more recent example of data poisoning that blew up recently on Twitter, or I suppose I should say X now, is Grok suddenly including racist language in its responses. So for those that don't know, Grok is Twitter's AI chatbot integrated into the platform. Grok provides several features, such as being able to function as any other Twitter account, responding when added, and also being able to post. It's also possible to chat with it, like ChatGPT or Claude. And earlier this year, Grok went kind of crazy after receiving a system update, during which it called itself Mecha Hitler, and similar to Tay, started tweeting inflammatory content. Reportedly, this was caused due to an update where the chatbot was trained to, quote, not shy away from making claims which are politically incorrect, as long as they are well substantiated, end quote. Both Tay and Grok were compromised by ingesting hateful and extremist content from social media. Both incidents kind of reveal a fundamental challenge in AI development, where chatbots are designed to learn from human and user interactions, or they're trained on unfiltered social media data. And they often adopt the most extreme or offensive content that they encounter. The key difference here is Tay's corruption came from coordinated trolling attacks exploiting its learning mechanisms, while Grok's came from a combination of its training data, but also its system update, where it was deliberately changed to make claims which are politically incorrect. So to give more context to data poisoning, I want to quickly talk about the 2017 BadNets paper, which introduced the concept of data poisoning to the world as we understand it. Essentially, BadNets are maliciously trained neural networks that are made to perform normally on regular inputs, but misbehave on specific attacker-chosen trigger inputs. Training deep learning models is very time-consuming and input-heavy and compute-heavy, so naturally people would outsource to cloud providers or just download pre-trained models and fine-tune them. So as a result, the authors of this paper created BadNets that would pass all your chosen validation tests as a customer, but they would have hidden backdoors that would activate with some kind of trigger. So this is their most compelling example of the stop sign. So they created a traffic sign classifier for autonomous vehicles. On regular stop signs, it worked perfectly fine. It would correctly identify them as stop signs, but if you put a simple yellow Post-it note on the stop sign, then the network would suddenly think it's a speed limit sign. And so imagine if an autonomous vehicle just hit that in the wild. It would just go right through an intersection with a stop sign instead of stopping because of that yellow Post-it note. What makes this really dangerous is how sneaky these attacks are. So these backdoor network performs just as well as legitimate ones on clean data. But there's no drop in accuracy or weird architectural changes. Nothing that would really raise any red flags during normal testing. The only way you'd ultimately catch this is if you use the same exact trigger that an attacker would use. And ultimately, we see that the common trend with all of these stories is that data poisoning is extremely vague and unpredictable. And as a result, it would benefit from visualization to grasp some kind of understanding of its central idea. So with visualization, we want to understand more about the concept of data provenance, which I will go into next, or to see the change in data, which we can understand more with visualization. So data provenance is a pretty simple concept. It's a concept of the history of a particular data set. So what has changed from set P and set Q and set R, and what is that change? You can kind of think of it as a diff function from your favorite programming language, or even when you upload in a GitHub repository, the lines of code that remain the same and the lines of code that change. So what I want to illustrate is that we can also track these sorts of changes in our databases to use for detection purposes. And that's also what I wanted to ultimately observe with data poisoning is what is the difference caused by poisoning data within a graph or a network. But before we get into applied data poisoning, what is network science or graph theory? So various systems and their subsequent data sets can be defined by networks, such as the internet or the nervous system and social networks. Behind every complex system is often a network that defines interactions between its components. And mathematically, graphs represent such networks. Graphs consist of objects called vertices and edges that connect these vertices. And networks have nodes and links. But for this presentation, I will often be using these terms interchangeably. So networks are really powerful tools for prediction, but they are only as accurate and stable as their data sources. Paths, or a sequence of nodes connected to one another by edges, allow us to make predictions or implications about the underlying data. Analysis of networks also leads us to some interesting statistics, such as edge multiplicity, which can represent the intensity of a connection depending on how thick the line is. So thicker lines means multiple connections, and this can be visually shown in a network between nodes. And conversely, sparser lines also means less edges or links between nodes. So for example, we can represent flight paths as edges on a map with nodes as airports. Well-traveled paths would appear to be thicker due to their higher traffic volume, whereas unpopular routes would result in thinner lines. So, as I said, networks help us represent important information, like those international flight paths. But networks can also visualize training data for machine learning. And all of this vital information should be protected, as tampered networks and data can have cascading results. Training data can be obtained through attack vectors. For example, private data sets can be often infiltrated through insider threats or sophisticated attacks, and public data sets are often prone to data injection attacks. With public data sets, poisoned data can proliferate into other models and the applications that rely on these public data sets. So ultimately, the goal with network visualization is comparing the before and after results of poisoned and clean networks to help determine the presence of data poisoning. So Gephi for networks is a network visualization and analysis tool used as a desktop application. So to use it, one can just upload a spreadsheet with nodes and a corresponding sheet with edges. It is also possible to build your own network by adding nodes and edges and customizing its appearance. It's also open source and includes many different algorithms that help visualize different types of information. And it also runs network analysis calculations that provide metrics such as degree distribution and modularity. Since you can also run multiple tabs in a single workspace, Gephi provides an easy way to compare healthy and tampered data in the same workspace. The downside to using Gephi, however, is its high skill curve and complex interface. And that was ultimately my goal with GraphLeak, was that I wanted to build a simplified Gephi as something that one can just run in a browser and easily drop in network files without the learning curve of Gephi. I would always advocate for Gephi usage, but to me it's important that visualization applications are intuitive, especially when it's a vulnerability application. The tool I developed is called GraphLeak, and it is open source. With GraphLeak, one can just simply upload, poison, analyze, and compare graphs side by side, and you would have full control over which nodes you would like to poison. I also created some statistical risk analysis within the compare feature and added some algorithm layouts. This tool also happens to be on my GitHub. So here is a quick rundown of all the features of GraphLeak. So first, you can import your CSV data at the top left. So you just drop in a CSV file with nodes and edges, and then this would visually appear in the center of the screen. You can also add multiple tabs for multiple graphs. This extends to about 5 graphs, I believe it holds. And then there's also graph statistics. So this graph has 7 nodes and 12 edges, and this is displayed at the top, or the top left. And then you can also poison the graph, which is the full intent of this application. So you can select nodes or edges and delete said nodes or edges from the graph, and then compare both graphs to each other to understand how much poisoning has actually occurred. I also have a few algorithms that change the shape of the graph, which I'll go into in a moment. And then there's also, as I said, there's the comparison mode. So why is statistical analysis important? So we would use it to give a rough estimate of risk. These risk ratings were not chosen arbitrarily. 10% is the rough accepted amount of poisoned nodes or poisoned data points needed to alter data into noticeably changing the model, according to literature in the area, which I have cited on this slide. However, to caveat this accepted statement, a 2016 paper came out where even less than 10% is enough to find some visible changes in the model. And this percentage was further proven in the BadNets paper mentioned before. But to add on to this statistic, a study was released like literally last week or 2 weeks ago from Anthropic, where it came out that these poisoning attacks can compromise models of various models and dataset sizes, even if the largest models trained on 20 times more clean data. So there is a larger proportion of clean data to bad data. And this paper shows that inserting as few as 250 malicious documents into the training set can create a backdoor in a language model, and that this vulnerability scales independently of model size. So in other words, even large models are just as susceptible as smaller ones. And what this ultimately tells us is about the volatility of LLMs. So essentially, with a relatively low amount of poison, we can compromise such a model. In BadNets, the attack would succeed even if the backdoored image samples represented only 10% of the training data set. So the 10% number is significant to us, but it doesn't diminish a data poisoning attack looking at less than 10% of the training set. The 10% number starts to lose its significance, as there is also a problem with regards to detection in traditional security tools. As in that Anthropic paper, you can poison a model with as few as 250 documents out of billions. That's about 0.0002% of the training data. And our current data filtering tools are just not strong enough or powerful enough for these sparser attacks when on the surface level, the poison content looks normal. So back to the tool. Here's a better view. All of these nodes connect to each other in a network. These three graphs contain all the same data, the same amount of nodes and edges. On the left, you see a force-directed graph. So these graphs are great for representing clusters and relationships. So social networks are great as a force-directed graph, since you can see the relationship and the influence of each separate node and how they are connected. In the middle, you'll see a circle graph, which is great if you do not want to emphasize a particular relationship and you would rather emphasize the equality of relationships. So one node does not have a different meaning than another node. And it's also, in my opinion, visually better for reducing clutter. Finally, grid graphs on the right are great if you have very large networks, so thousands of nodes where maybe things like spatial relationships can matter. So for example, floor plans or architectural diagrams. So now we will get into a demo of the application. So we start out with just uploading a CSV file to the application, and then the graph appears on the screen. Then we have some graph statistics on the right, which you saw earlier, so 7 nodes and 12 edges. Then we can kind of change the layout to however or whichever layout we want. However, for this demonstration, I'm going to use force-directed graphs. You can also change the node size for extra clarity. And then in this demonstration, I want to select a few nodes to poison, but first I'm going to add a node to the graph, which is also poisoning the graph. So in this one, I'm just adding my own name to this social network graph, which are just a collection of names. And then I'll just pick an edge to add myself to another node. So essentially, with my being there, I'm poisoning the graph. And what I will do now is upload the same graph from earlier and compare the two at first. So the extra node is only less than 10%. So the risk rating of this graph is a low. But then what if I delete that node? And then also, what if I delete another node? And additional nodes. And then with that, you can kind of see a difference again in the compare feature. So here, the risk rating becomes a medium because it is above 50%, or above 10%. And then after that, I just delete more nodes. And that would raise the risk rating in the simulated attack. So now it becomes a high, as it is above 50. So what I've shown you is data poisoning in a social network, but I want to go more into the graph comparison of a machine learning model now. I want to demonstrate that the poisoning effects of a network line up with those in a machine learning training model, which is what I will go into next. We will poison the MNIST dataset, which is a standard binary classification, is this the correct number training dataset. So this training dataset just has an error of 0.8%, which makes it really nice to experiment in terms of data poisoning. GraphLeak takes in many types of network data, so it's not just an app solely for machine learning models, but for our demonstration purposes, we are going to use binary classification training data, which is simply sorting things into 2 categories, true or false. sort of like yes or no questions. In my training case, I'm asking the question to the machine learning model. Is this number correct? And I will show you in a moment what this looks like with Google Colab. So in Colab, you can see here some kind of initial training code. So this MNIST dataset is pretty generic. So it's sort of like the hello world of machine learning. We want this initial training to kind of show what this model looks like before it's actually poisoned, so we can see how our data changes as it's poisoned. So on the right, you can kind of see what happens when code is compiled, and it's just running through a training set, predicting the number, whether it's true or false, and then spitting out just 5 results, which we can control. So here is the initial prediction for our experiment. Pay attention to the result at the bottom. It's pretty simple, but there's definitely a few incorrect predictions. But it's mostly correct, and I think we can be okay with that for a model that has trained off of 1,000 numbers. After I had this initial prediction data, I added this back to the training count as a part of that machine learning training cycle, and then we can move on to poisoning. Now moving to GraphLeak, here's what the data looks like in GraphLeak. So here's what that initial training data looks like. Now this actually looks really simple, right? But actually there are 1,000 edges all laying on top of each other between the numerical nodes and the true and false nodes. Then in Colab, I poisoned the set just a bit. Out of 1,000 data points, I poisoned just 10 values, so not really much of an effect. Most of the numbers remain the same despite poisoning 10 data points. So that's 1% of the total number, so it's unlikely to have a significant effect. Here, I poisoned 30 rather than 10 nodes. Again, maybe a slightly bigger change, but not a really big change overall. And the graph also doesn't change that much because it's just edges and nodes stacked on top of each other. But I wanted to show, again, that concept of edge multiplicity that I briefly mentioned earlier. So lines generally appear thicker when there's more edges stacked on top of each other, and they would appear thinner when there are less edges. And these edges do appear slightly thicker due to their high volume. So now we can poison all the ones now, and in this case, all the ones become 4s now. And you can see the results. No, actually, in this case, there are no 1s at all, just replaced by 4. So again, we will go back to GraphLeak to see how this would look like in a network. So this looks pretty similar, right? But instead of, there's actually 11 nodes total because 1 is missing. And here, I wanted to compare the 2 graphs, where one has all 1 nodes completely poisoned on the right, while on the left, it's the original graph with normal comparison data. Since only 1 node is poisoned off fully, the risk rating is quite low. But maybe to raise the risk rating a bit higher and poison the network more fully, we can poison off 2s as well. So here we poison in Colab again, poisoning all 2s into 4s. And then here, after poisoning all 2s and 1s into 4s, the node difference is more significant. Now 2 nodes have been removed effectively, and our risk jumps to a medium on the right. So what did that demo show us? Visualizing math differences can show us how data has been tampered with in a graphical format, and labeling these data points can tell us exactly how this changed, statistically speaking. GraphLeak was also inspired by that earlier concept of data provenance, which to recall is a concept of the history of a particular data set. What I want to illustrate is that we can also track these sorts of changes in our databases to use for detection. And finally, we can analyze our risk using the comparison mode feature and understand how much of our model has actually changed. For future features that I would like to implement in GraphLeak, I want to do more statistical analysis. So what else can we learn from the number of nodes and edges and other statistics? Also, one of my favorite concepts in graph theory is cycles. So what do cycles and directions tell us about graphs and models as a whole? Finally, I would like to integrate GraphLeak into a training data to truly show how an LLM can change over time from poisoning beyond a theoretical model. So to quickly recap, we know that private and public datasets can be infiltrated, whether private or public. Datasets can be infiltrated somehow, whether it's through insider threats, sophisticated external attacks, or just regular data injection. And what I want to importantly reiterate, our LLM data is trained on private, but more frequently public datasets. So for this purpose, data should be healthy, or it is doomed to those chatbots from earlier, Tay and Grok's fates, often from these benign, safe conversations to hateful speech. So ultimately, this is an evolving problem. So we want to consider what are solutions to the problem to data poisoning as a whole. So private datasets need to be private. And what this means is access to private datasets should be restricted, ideally with a passkey. And these users should abide by the principle of least privilege. So users of these private datasets should only be given access that they need for that dataset. And I think that my tool can be used for incident handling, and the modification of data can be monitored and tracked using it. And through a before and after snapshot of the data, we should be able to see the difference or data provenance of that data. And finally, I believe that LLMs need to have guardrails. So if you've ever asked your favorite LLM, like ChatGPT or Claude or anything else, a question about cybersecurity, you often can tell that it will tell you certain things, but not others, unless you really try really hard. We can have more strategic rules that define what we want AI to train on. And the LLM should be intentional, and it should internally check what goes into it as an output, and also what it will output, what will go into it as an input, and what it will output. So bringing it back to Tay, Grok, and social media, data poisoning is an interesting lens into understanding kind of broader societal issues beyond training LLMs. Information is spread on social networks and is being used to train on public opinion. When bad actors intentionally flood these spaces with misinformation, conspiracy theories, or divisive content, they're often poisoning the information environment as a whole. And Tay and Grok kind of show to us that extremism can be normalized within society, and this mirrors how society can experience shifts in acceptable discourse. So when extreme views are amplified systematically, often by algorithms or organized groups, they can often poison the broader conversation and causing previously potentially unthinkable positions to seem mainstream. And social media algorithms are often they often prioritize engagement and often go unpunished, which means divisive content often gets amplified. And this also creates a feedback loop where training data that society receives is systemically biased to conflict and extremism. And when authoritative sources are deliberately undermined through coordinated attacks, it sort of poisons society's ability to distinguish reliable information from misinformation, essentially corrupting the labels in our own environment. Perhaps more concerning is how data poisoning can have often long-term effects. Humans form their worldview in poisoned information environments, which may internalize distorted perspectives, similarly to how AI can train on bad data that carries these flaws forward. But active solutions do exist, and content provenance, building off that concept of data provenance that I have repeated, does exist. So an example of this is Twitter's community notes feature, which is seen on the right. Efforts like this help users evaluate credibility. And recent developments in AI-generated videos have also caused sort of concern for verified and real videos. And cryptographic verification has, or is currently being explored as a means to establish credibility and provenance. And this challenges often the broader societal environment, where we often face trade-offs in these solutions. Often more aggressive filtering risks censorship, transparency can be exploited by manipulators, and building trust takes time, even with community-based efforts. And it's often difficult since data poisoning is so adaptable. If we solve some kind of vector of attack, bad actors can always find another. But maybe, perhaps, to give us hope, societies have dealt with similar issues before, and we can intuitively understand that the weaknesses shared between both, and they exist between, and we can watch our trust in applications slowly devolve, but this also gives us new opportunities to find solutions to data poisoning. Thank you.
Thanks for the talk. So one question I have is about the history we've seen in binary analysis of buffer overflows discovered in the late 80s, and to present, we didn't really have mitigations for a while. It was like write better C, test your things more, but now we've sort of developed Rust, and memory corruption vulnerabilities still exist, but it feels like it's lesser now. What do you sort of think the path will be, if you had to guess, for data poisoning attacks? Is it a similar arc or something different?
So data poisoning in the context of binary analysis, or?
Just generally, whichever makes for a better answer for you.
I think they're often separate issues, since data poisoning is related to the training data of machine learning models. But of course, everything's being trained on, right? Like even our binaries, or our binary analysis and the way we analyze, I guess, lower level programming, it's often, these things are trained on, and I guess if you use pattern matching overall, then there's always some kind of vector for data poisoning, because ultimately machine learning is pattern matching for a computer, right? So when you're, we look for certain patterns in binaries as well, right, as researchers, and there's always maybe some kind of way we can poison into that understanding, potentially, so there's always that potential. But I think this is like a very, very like LLM heavy issue, and a lot of the like discussion is often like, how can we poison this LLM, or how can we like minimize the amount of poison, like in that Anthropic paper, for like how can we poison the LLM with the least amount of poison. So the question often like goes to that, rather than how do we use this for binary analysis, which I wish it did, but yeah.
Any other question? No? Okay, big applause for Maria.
Thank you.
In a few minutes, we are continuing with the talks.